Hello! In this video, we're going to look at how we can apply the linear combination of atomic orbitals to start solving the Schrödinger equation for the H2 plus molecule, which is the simplest molecule that we can make. So the learning objective here is to determine the Hamiltonian and overlap metric elements for the H2 plus molecule and relate them to the Coulomb, resonance, and overlap integrals. So what is this H2 plus molecule? Again, it's the simplest molecule we can make. It's two protons, labeled A and B, and one electron that keeps them together. By the way, this molecule exists, so it's not that we're making up things. It's not very stable, but it exists. And so that is a reasonable case study for us. What is the electronic Hamiltonian after, throwing away the nuclear kinetic energy, nuclear repulsion, because Born-Benheimer approximation, where we are left with two terms, the kinetic energy of this one electron and the electron nuclear attraction to atom A, 1 over Ra, by the way, we are in atomic units here, and to atom B, 1 over Rb. We don't even have the electron and electron repulsion 1 over Rij, because there is only one electron. This doesn't make this example any relevant, it just makes it easier to work with and understand. So again, we need to solve the Schrödinger equation to get the electronic energy. So what are we going to do with this psi of R? We saw in the LCAO approach that we are going to describe that as a Slater determinant of spin orbitals formed by a spatial part and a spin part. And what are these spatial parts? They are molecular orbitals formed by a linear combination of atomic orbitals. So let's see what happens specifically for the hydrogen 2 plus case. How is this Slater determinant going to be for the H2 plus case? Well, for the H2 plus case, I have only one electron to place, so I need to form only one molecular orbital phi, I'm going to call it phi 1, of that one electron, and associate it with whatever spin I want, alpha or beta, to turn it into a spin orbital. So that's a very boring Slater determinant, just one thing, but that's good enough for me. One cell, that's good enough for us. All right, so now let's see what this molecular orbital phi 1 looks like. I'm going to label it phi I to be general, because we're going to see that eventually we can make anti-bonding orbital and things like that, but for the moment we want to be general. I label it phi I. Of this coordinate of this electron, I have only one electron, so I'm going to not even label it R1 anymore. I'm just going to label it R. And it's a function of these atomic orbitals. Again, a linear combination of atomic orbitals centered on each atom. And we are weighting each atomic orbital with these expansion coefficients. So let's see how this is going to look like. So we're going to have, for the H2 plus molecule, this molecular orbital, I'm going to drop even the label I, formed as a linear combination of our only two orbitals that we can deal with for a diatomic molecule that has only one electron. We're going to use an atomic orbital of 1s type centered on atom A with a coefficient Ca, and combine it with an atomic orbital centered on Cb with a coefficient Cb. That's our linear combination of atomic orbitals for the H2 plus molecule. So let's see how this looks like. So this phi A is a 1s orbital centered on atom A. So it's going to be some normalization coefficient, I'm not even writing it, and our usual exponential decay with a parameter theta that can be optimized. And Ra is the distance between the electron to atom A. And that's how our theta A is going to look like. I put in coefficient only on atom A. And for theta B, I'm going to do the opposite. I'm going to center it on atom B, and I'm going to make a molecular orbital by making a combination of these two atomic orbitals. Alrighty, so here we are, again, recap, electronic energy, electronic Hamiltonian. We have the same terms that we've seen before, and now I'm rewriting our molecular orbital, and I'm just color coding the A and B in green and pink atomic orbitals, because it's going to be clearer in how these things pan out in the next equations. So how do we solve this Schrödinger equation? Given the fact that we guessed a lame wave function, we know it's bad because we know it's not going to be right. While in the helium atom, we use the variational principle. It was telling us that whatever wave function we can come up with, its energy is going to be greater or at best equal than the true energy. So we're going to use the same here. And so we're going to calculate our expectation value for the energy. I'm going to put my wave function, the electronic Hamiltonian, again, the same wave function, that is this one here. And then to make sure that even if the wave function is not normalized, if I divide by the overlap of that wave function, I'm going to make it normalized. So that guarantees me that even if I don't normalize the wave function, it's going to turn out like it were normalized. All right. So what are we going to do next? We take this phi here, we plop it in here, we plop it in there, we plop it in there, we plop it in there, and this is what happens. And so that's why I color-coded it. So from each term, numerator and denominator, I can generate 4 terms. Green to green, green to pink, pink to green, and pink to pink, operating at the numerator with the electronic Hamiltonian, and at the denominator is just going to be an overlap integral. So what are we going to get out of there? Well, from green to green, I'm going to get this CA squared, because this theta, CA squared, and then I'm going to have this theta A, HE, theta A integral, and we're going to see in a minute how that looks like, and then we're going to have for theta B to theta B the same, and then we're going to have the two mixed terms, theta A Hamiltonian theta B and theta B Hamiltonian theta A. I have the 2 of those, so that's this term here. At the denominator, things are exactly the same, except that at the denominator we don't have an operator, we just have the overlap that we're calculating, and because these thetas are atomic orbitals that are normalized on that atom, that theta A to theta A integral is 1, that's why we're left with this coefficient squared. And then we're going to see in a second what this SAB is. So far so good. Let's look at what these terms that arose are. So HAA is the same as HBB, and is nothing else than theta A, electronic Hamiltonian, theta A, integrated over all of the space. So that is one of the matrix element, one of the integrals that of the Hamiltonian integrals that we are looking for. The mixed term is very similar, but now we have theta A, the Hamiltonian, theta B, so the orbital center on theta A, integrated over whatever I'm getting after I apply the electronic Hamiltonian to theta B. And finally, we have this overlap integral, theta A integrated, multiplied by theta B, and integrated over all of the space. So these are the 3 terms that are described here. And because they are kind of symmetric in a way, HAA equal HBB and HAB equal HBA, because of the fact that H2 plus is a symmetric molecule, it's not like HCl or HO, and 2 sides is going to be the same. Therefore, I can even further simplify this by grouping these 2 terms in there and by grouping these 2 terms in there. All right. Last thing we need to do is to look at what these 3 terms here are in practice. So we call this SAB the overlap integral between the atomic orbital A and the atomic orbital B. So what is this looking like? So we have in 2D slice, remember this is always 3D thing, so there are still the spherical harmonics there, but in a slice of this 3-dimensional surface, we can look at the orbital centered on A as this green line, the orbital center on B as this pink line. We take the product of those 2, theta A times theta B, is this black line down here. And then we calculate the integral over all of the space, and that's the gray shading under the curve. So that gray shading under the curve is SAB. Again, remember, this is just a two-dimensional slide. That's not all the integral. There is, integral that goes all around the 3D surface. But on a 2D slice, to understand what's going on, I think that should be sufficient. So that's what the overlap integral is, and it tells us how much in common these two atomic orbitals that are centered on different atoms are, how much in common they have. All right, next let's look at this HAA term, which is what we call the Coulomb integral, and we label it J. And let's work it out. When we apply this Hamiltonian in here, we're going to get a term 1/2 kinetic energy 1 over Ra applied to theta A. Well, that's nothing else than the electronic energy of an electron centered on atom A. So that's why I call it EH. What is left is the interaction of the electron density centered on atom A with the nucleus of atom B. And so that is what this Coulomb integral J is. It's the interaction energy of the electron density centered on atom A with the nucleus on atom B. And the flip side of the coin is going to be exactly the same in number, is the interaction energy of the electron density centered on nucleus B with nucleus A. That is the Coulomb integral. We are almost there. We have one more integral to take care of, which is this resonance integral. And when we apply this Hamiltonian to this equation here, we get out still the electronic energy of the hydrogen atom. Now, because the two indexes here are different, it's going to be scaled by this overlap SAB. And then we're going to have this resonance integral here, which is something weird. It's the interaction of the overlap density, so that the grade area between atom A and atom B, so the electron density that is shared by the two atoms with one of the two atoms, but it's the same distance, either atom A or atom B. Here in this case, it's going to be atom B. So we have seen in this video how we can apply the linear combination of atomic orbitals to the hydrogen atom. We have seen that it the H2 plus atom. We have seen that it simplifies greatly in a way that we can analyze all of the matrix element HAA, HAB, and SAB overlap integral that arise from solving the Schrödinger equation to calculate the expectation value for the energy. And we have seen there are three terms that arise: the overlap integral SAB, the Coulomb integral J, and the resonance integral K. Armed with all of these tools, one can then next solve these equations here. We're not going to do that now. And solve actually for the expectation value of the energy and try to minimize that by changing the coefficient and using the variation principle. Already.